Show that the function f of x equals x to the fifth plus 10x minus 4 has exactly one real root and that it lies within the interval 0 included to 1 included. The first thing to do is to determine whether the condition is met for the intermediate value theorem to apply. The function f of x, which is x to the fifth plus 10x minus 4, has to be continuous on the closed interval given. Well, x to the fifth plus 10x minus 4 is a polynomial. And a polynomial is continuous on any interval, so it will be continuous on the closed interval given. Closed means it includes both endpoints, indicated by the square brackets on both endpoints. The condition is met, and therefore the intermediate value theorem does apply here. Before stating the conclusion of the intermediate value theorem, we will want to evaluate the function f of x on each of the endpoints of the interval given, 0 to 1, f of 0, and f of 1, since these will be part of the conclusion of the intermediate value theorem. F of 0 will be 0 to the fifth plus 10 times 0 minus 4. 0 to the fifth is 0, 10 times 0 is 0, and then minus 4. 0 plus 0 is 0, and then minus 4 gives a negative 4. F of 1 will be 1 to the fifth plus 10 times 1 minus 4. 1 to the fifth is 1, 10 times 1 is 10, and then minus 4. 1 plus 10 is an 11, minus 4 gives 7. The conclusion of the intermediate value theorem is f of x equals y for each y in the closed interval made up of f evaluated at each of the endpoints, which gave a negative 4 and a 7. The lesser one written first, the negative 4. The greater one written second, the 7. For each y in the closed interval negative 4 to 7, at some x in the closed interval given 0 to 1. What this says is the function will hit every single value between negative 4 and 7, including the endpoints, at least within that interval, perhaps even more, but it's guaranteed it will hit every value in that interval within the x values of 0 to 1. So the function will hit every value between negative 4 and 7. Since the left endpoint is negative and the right endpoint is positive, one of the values that it will hit between a negative and a positive is 0. So one of the results of the intermediate value theorem is that the f of x will equal 0 at some x in the 0 to 1 interval. F of x equals to 0 is the exact definition of being a root, and this is occurring for some x within the 0 to 1 closed interval. So another way to state this is f of x has a root, and that root is residing somewhere in the 0 to 1 closed interval. So that shows that f of x has a root in the closed interval. We now need to show that it has exactly one root that lies in that interval. The intermediate value theorem will just show that it has a root in that interval. To show that it has exactly one root, we will need to make use of the mean value theorem. For the mean value theorem to apply, we have to show the two conditions. One of the conditions is the function has to be continuous on the closed interval given. We've already showed that. It's the same condition for the intermediate value theorem. The second condition is the derivative. Let's find the derivative of f of x, f prime of x. f of x, the first term, x to the fifth, will be a power rule. Bring the power down, subtract 1 from it. Second term is a constant times x. Derivative will be the constant. Third term is a constant with no x. The derivative will be a 0. The derivative has to be continuous. It's called differentiable on the open interval. Well, the derivative, 5x to the fourth plus 10, is also a polynomial, and it's therefore continuous. It's called differentiable on any interval, including the open interval from 0 to 1. We want to put this on the open interval because a function is never differentiable on its endpoints. So this is always on the open interval. But both conditions hold true. The function is continuous on the closed interval and differentiable on the open interval. And therefore, the mean value theorem does apply. The conclusion of the mean value theorem is that the slope of the tangent line at some value c, f prime of c, equals the slope of the secant line connecting the endpoints, f of b minus f of a, over b minus a. F prime of c can be evaluated by plugging c into f prime of x. That will give 5c to the fourth plus 10, and that equals to f of b minus f of a over b minus a. Let's look a little bit closer at the derivative evaluated at c. 5c to the fourth plus 10. And let's find where this might equal to 0. Let's subtract 10 from both sides. 5c to the fourth equals negative 10. Divide both sides by 5. c to the fourth equals to negative 2. And now take the fourth root of both sides. When taking the fourth root, just like the square root or any even root, we end up with a plus or minus. And it will be the fourth root of negative 2. Just like the square root or any even root, the fourth root of a negative number is not a real number. And therefore, we have no real number that makes the derivative equal to 0, so the derivative cannot be 0. Back here with the mean value theorem, if the derivative can't equal 0, that's the left side of the mean value theorem. The right side, the slope of the secant line connecting the endpoints, also can't equal 0. Now, if this fraction can't equal 0, we can multiply both sides by b minus a. And f of b minus f of a can't equal 0. And then adding f of a to the other side, f of b cannot equal f of a. What this says is the function cannot equal itself at two different x coordinates. So if we have f of x equals 0, which we've established already does happen in the 0 to 1 interval, it can only happen once. The function can't equal its same value at two different x coordinates. So if we have it equal to 0 at one x coordinate, it can't be equal to 0 at another x coordinate, which means that it cannot possibly have another root. So the conclusion of this is that f of x has exactly 1, and it's a real number, so we can state the word real in here, one real root. And we've already found the interval that it lies within 0 to 1, closed interval. So we've shown then completely that f of x has exactly one real root, and it lies in the interval from 0 to 1 with the endpoints included.